Okay, thank you. Good morning, everyone. So my talk will be complementary to talk of Chris Belczynski. That's just because you have in your plan Chris Belczynski. So here I will focus on this technical side of simulations, which results were shown in previous two talks by Chris. This is this population synthesis side. Some people say it's a dark side of these simulations. Yeah. So in this first part, I will do an introduction to this method, and in the second part, we will have a hands-on session to work on this data and get some results connected with double compact objects. The short overview of what we are going to do today is we will start with an explanation, a very short explanations without going into very complicated details of the simulations, but we will explain the idea and the methodology which goes after obtaining these results for populations of stars. We will discuss this stellar environment which have a huge impact on the results. Some things like star formation history can be applied in a post-computing. So you have already a simulation done and you can change the star formation history to obtain results for different stellar environment. That's what we are going to do today. Some other factors like metallicity or initial mass function needs to be applied during the computations. So we'll have a few files to use them, but we cannot change them after performing the computations. And other factors like binary fraction, total stellar mass, which was simulated, are used for scaling, because we cannot simulate entire galaxies. Even for such methods like population synthesis, it's too much. So we simulate some fraction, some representative fraction of a galactic disk, for example, and then we scale these results to be comparable with observations. And then we'll go to the estimations of merger rates from these calculations, and also we'll see some parameter distributions in this hands-on session. So before I start, I would like to ask you who is familiar with population synthesis method? Are there people here? Okay, one people. Okay, great. So I hope it will be very interesting for you, and maybe you will find it useful for your work. So let's start. As there are many people using population synthesis codes, there are also as many definitions of population synthesis. Usually every scientist has its own definition of what population synthesis really is. Sometimes these definitions really are different for different uses, but there are some characteristics which are in common for all of these methods. First one is the main one, is that we do not use detailed evolutionary codes for stars, but we use fits to the results of these detailed evolutionary codes. And what's the important gain is a high speed up of computations. If we take a detailed evolutionary code, for example MESA or Geneva code, we can simulate several types of stars. We can do tens, maybe hundreds of these stars, but in some reasonable time, like month. But even these hundreds of stars, which we can simulate in this reasonable time span, still are nothing in comparison to realistic star populations. With population synthesis codes, we have such a speed up that we can compute any evolution of any system in seconds. So within a month, we can compute millions of systems. And this number is already comparable to these large stellar populations, unless we are looking for really rare objects. This also gives us the possibility of investigating variety of models, and that's what is most often done with population synthesis. So we use this speed up to simulate a large variety of models, especially in these things which are not really understood perfectly in stellar evolution, like this famous common envelope phase. And we can compare how these different models influences the results of computations. So usually a typical number of stellar stars or binaries we need to simulate is around 1 million, but sometimes it's higher. What matters is how many interesting binaries you get. You try to fine-tune the initial populations to get as many interesting systems, in our case double compact objects, as it is possible. But even though most of these systems either merge too quickly or are disrupted, you get some populations of these objects that you really want to investigate, and then you check if this statistics is good. And to avoid integrations, especially of initial distributions of parameters, we use Monte Carlo sampling of distributions like initial mass function or natal kicks for compact objects. This is another speed up gain for these computations, but on the other hand we lose this precision. We need to still fine-tune this number of objects we want to simulate to have such high representation to avoid any numerical and statistical high numerical and statistical errors connected with this Monte Carlo sampling. There are of course limitations of this method. For example, we cannot do it for objects which are interacting. So no one have done at least for a large scale Monte Carlo simulations of globular clusters, where these interactions between stars seems to be of high importance. However, in galactic disk, we can assume that interactions between stars are so rare, or they are unimportant for these systems, these close binaries we look for, that we can assume that all these systems evolved in isolation. There are many codes which use population synthesis methods. Some of them I listed here, but there are many other codes. Usually they differ only slightly, and the difference comes from the fact that they are written with an intention to work on some kind of objects. For example, double white dwarf mergers. In our case, the Star Trek code here in the middle was written with a particular attention put on massive stars. So that's why it is a good tool to use for investigation of double compact objects and their mergers. But still, when we want to simulate millions of binaries and a large variety of models, we need a huge computational power, and as you know, the computational power of clusters, especially these university clusters, usually is hard to obtain. So a small advertisement here. It is our project. Have any of you heard of it, maybe? Oh, yeah, one person again. Great. So, Universe at Home, what's the idea? It may be also interesting for you to do something similar for your projects if you need huge computational powers. There are millions, if not billions, computers worldwide. Most of them, like your laptops, are not very useful for large-scale simulations. But when we combine all these small computers together, we get such high computational power that we can compare with computational clusters. So here we just want to use distributed computing on these small machines to get high computational power which are independent from these clusters and all the bureaucracy which is necessary to get these your computations done on these computers. But how to get to this large number of computers? The idea is to ask for participants worldwide who have their computers and usually don't use their computational powers, like probably most of us here currently are just writing something, coding something, and not running some demanding computations or demanding 3D games which needs all the resources of your computers. A small program may work, a small part, small chunk of a simulation in the background of your computers. You will not even notice it because it will work with a very high nice factor for your system, and whenever you want to need to use your computer, it will just suspend and restart working when your computer is again available. So you lose nearly nothing. Of course, your computer works, so it uses energy. So your your price of your energy may rise after it, but maybe it's not so important as the satisfaction you have to be a part of a large computation and make a universe on your computer. Yeah. So our small achievements so far is 24,000 participants, which give us more than 100 teraflops of computational power. For these of you who are not familiar with this unit, teraflops are trillions of floating point operations per second, and if it still is not something which describes how large computational power it is, largest computer working currently have petaflops of computational power, so just 2-3 orders of magnitude higher than this thing here, and we have just 24 participants. These participants are slightly biased because they are mostly people who are IT guys or who are administrators of some SQL databases, so have hundreds of computers and they connect them to our servers. Yeah, so we are very thankful for them. But this method worked for us, and as Chris said yesterday or the day before, we were able to compute more than 10,000 of models for our computations, which give us a very interesting in-look into the importance of parameters for the study of compact object mergers. But now, where our data is available. So there is another project which is just for storing data. You may take a look at this page because soon we will download data from them to put our hands on it. It's called Synthetic Universe, and to get to the data we will be looking on today, we need to click on Download, Double Compact Objects, and later Local, and we should get something similar like this one here. So what we'll have here is a description of the data files, which are available slightly below this screen. All data files are similar. We have a record. Each record is for one compact object, which is a double compact object, which is formed at the moment of formation. So the second supernovae, formation of the second compact object. Here you have also description of all the parameters. These files are used for different studies, so that's why we have so many of these parameters. Actually, there are at least 4 times more parameters, but we do not provide them to have smaller databases, and they are not important for people who are not working precisely with simulations. What will be important for us is T-del, the delay time. It's probably the 6th or 7th value in this record. Is the time since the birth of the system, so when both stars are on their ZAMs, to the merger of the compact object. Some details of these simulations, which are described in a paper. It's long, so I don't ask you to read it now. So I pointed them out here for you. We simulated 2 million binaries for each of these models. The parameters we use for metallicity is the solar metallicity and 10% of solar. And we provide here 2 treatments of the common envelope phase. This one which Chris described yesterday. The optimistic one, which allows for common envelope where donor is on its Hertzsprung gap phase, and B model, the pessimistic one, where these common envelopes are assumed to merge always. It's pessimistic because, as you will see, we always get lower merger rates in these B models than in A models. We have also other varieties there, probably about 15. They don't have fancy names, they are just called variety 1, 2, and so on. They are described in a paper. If we'll be very quick today, maybe we'll also look into these variations. And I mentioned the scaling factor. It's necessary when we want to translate these 2 millions of binaries, which is a very low number in comparison to our galaxy, to real stellar population. What we name a scaling factor is just a total stellar mass of a system we want to compare to. In our case, in our hand-on session, it will be a Milky Way galaxy, and total stellar mass of the simulation. In these simulations, the total stellar mass is about 7.3 times 10 to 8 solar masses. It depends on how we use the initial mass function, what binary fraction we apply, and so on. But but today we'll not play with these parameters. We'll try to play with star formation rate. And merger rates calculations. I'm sure that you were talking about it for long, and you have more elaborated formulae for calculating these merger rates. But for our needs, this simple formula, where we just count the number of double compact objects which merge within the current time, and there is a time range which is marked with delta t here. We need to use this delta t because if we put 0 here, the probability that something will happen in the direct moment is always there, no matter what star formation rate you choose, unless it is some Dirac's delta or some other fancy function. So we need to put this delta t here, and we need to do it properly. And usually it's a kind of fine-tuning to find the best value of delta t here. If we put it too small, we may want to get as current merger rate as possible, but on the other hand we have a very high numerical and statistical noise. When we put it too large, we just obtained the average merger rate for this large time. So we need to find some golden mean between these two extremes. And what star formation history give us is just the birth time probability. This birth time probability, together with this delay time we get from the simulations, give us this time of a merger which we need for this computation of double compact object merger rate. So, if probably the questions will appear now, because what we would like you to do with Chris is to calculate merger rates and parameter distributions like total mass, mass ratio, separation, evolutionary history for these models which were computed with the population synthesis code StarTrack, and just see how these parameters and merger rates depends on these values. There are, of course, simplifying assumption we can take in a first step. The total stellar mass for a Milky Way galaxy. Of course, there are many estimates. Sometimes it's 2 times higher value, sometimes it's 3 times lower, but we can take this value if you have nothing which you think is much better than this estimate. We can assume that the star formation rate is constant through 10 billion years of galactic evolution. Once again, it's of course not correct. This star formation history for our galaxy is much more complicated and it's not uniform for the entire galaxy. But just to see how these parameters work for these populations of double compact object, we can assume at first step this star formation rate. And delta t, this one from this previous slide, we found that a good estimate which gives good results for this star formation rate is about 1 gigayear. If you use these simplifying assumptions, your results can be compared with this presented in a paper which is cited on this web page, on this database. However, later on we can start to improve these assumptions, or we can do some more fancy thing like burst-like star formation rate and see how the merger rates will change throughout the time when we are in the burst of star formation, and what happens when we are after the star formation burst, how the merger rates change. And of course there are model variations. If you have already checked this web page, you will see that there are many of them and we can check them, how they work. Too simple? If we can do it in 5 minutes, we can go for lunch. Okay, yeah. So, any questions to this? Yes, on this web page it is the description of the data files. If something is not obvious, just ask. So I will be here to help you, and we can if when you get some results, this first one may be very straightforward, so we can compare what we get and see what are the. Okay, yeah. So maybe I will write it here. Yes. Yes. Yes, exactly. Okay, okay. I now know the question. So here in population synthesis codes, we assume that binaries are already born to, as a binary. So we don't have these interactions. We have no other way of forming binaries. We assume that already from molecular cloud we form binaries. So both stars have the same age. Yes? Yes. So first let's look at standard model. Yes. So yeah, so I hope that it's also written on a page that these data files are named in this way, that we have a first letter which describes how we treat common envelope for Hertzsprung gap stars. It's A or B. Then we have black hole, black hole, black hole, neutron star, or neutron star, neutron star. So it describes different types of compact objects which is already prepared for you. And the last number, which is 002 or 002, describes either a solar metallicity or 10% of solar metallicity, respectively. So we can calculate merger rates separately for these types of double compact objects, and then we can sum up them to have total merger rate. Yeah, so these files are already prepared for calculations of merger rates. So if you don't have your computer with you, feel free to go and bring one. Yes. Yeah. So we want to count these double compact objects for whose the merger time calculated in this way as a sum of this delay time which is provided in these data files plus this birth time which is given by star formation rate. So we need to sample this star formation rate either in a Monte Carlo method or calculate the probability for the birth time to be accurate for the this merger time to fall into this range. So either we use this Monte Carlo method for sampling star formation history, or we can calculate probability. What's the probability that the system will be born in a time accurate for appearing as a merger for us? Okay. Yeah, so there are many things we can do. The most interesting, I think, are these merger rates. Yeah, but also interesting are these parameter distributions, which can just be taken from these data files, and we can see what's the total mass of double compact objects, or the chirp mass, which is also already calculated for you in these files. And we can do it for the entire sample of double compact objects, and then compare them to these double compact objects for which the merger time is below the Hubble time, and we can check the difference. We may also check the difference between different types of double compact objects, but probably this is the most interesting in the light of these merger rates. Yes. Yes. Okay. When you go to the web page, yes, up, and here you have how looks the record in a data file, and here are all the explanations. So first are masses, then we have separation and eccentricity. There is also this T-del, which is this delay time. This is from the birth of the system to the time of the merger. Okay, so just to repeat here on this in this database, when you download a file, you will have one record for every system which was calculated, and in this line here below, we have all the parameters which are provided for this compact object, double compact objects at the moment of formation. So after the second, just after the second supernovae, and here we have descriptions of all the parameters which are provided. The seventh one is this delay time, T-del, which is most important for merger rates calculations. The last one field, as you will find it, not all records have the same number of fields, because the last one is the evolutionary history of this system, which tells us what were the evolutionary phases before the formation of these double compact objects. These are these nice plots that were shown yesterday by Chris with graphics. Yes. Uh, Once again, what was the question? Yes. Okay. So NDCO is a number of double compact objects. We can focus on one kind of double compact objects, for example, neutron star mergers at a time, and we only count these double compact objects for which this merger time is between the current time and the current time delayed by delta t. So delta t years ago. We need to give some spread, and later on we divide it by this spread to get a merger rate in time and not the number of objects. So this gives us actually the average merger rate during this delta t time. But when we calculate these merger rates for constant star formation rate, this delta t can be large, so we obtained very low statistical and numerical error. That's what I propose to use at first. Later, you can experiment with much lower values and see how the merger rate will fluctuate between different. When we use Monte Carlo sampling, it which will fluctuate strongly. Yes, TDEL is something which needs to be calculated because it depends on evolution of binaries. Okay, so it's not T-merger, it's T-mer, yes? Yeah, so these are different things. That's why I put it here, because T-merger, it's time from the formation of the double compact object to time of the merger. I think it's T-merger. Yes. These are very similar, but the difference is the evolution time of till ZAMS to the formation of double compact objects. So TDEL, this delay time, is from the formation of the compact objects from the birth time of the binary to the merger. Whereas merger time is not from the formation of this T-mer, which is provided in the data file, it's not from the formation of the binary, but from the formation of double compact object. So it was the other way around. Okay. Okay, so T-birth is something which is most problematic here, and it depends on star formation history. When we assume that star formation history is constant, the birth time of any at any time is equally probable. So Either we do a Monte Carlo sampling and just draw from this constant uniform distribution the birth time for any of these systems. Either we calculate a probability from this star formation rate that the birth time will be good for this merger time to be within these limits. So to help you, if it is a help, if you want to use this probability approach, which is more which gives better results because as many times you calculate it, the probability will be the same, but it's slightly harder to to write it down in a code than Monte Carlo sampling. Yes. Yes. Okay. The n simply without. Okay. So we have this delay time from our data file. So what was calculated? This birth time we need to get from star formation history. When we assume this constant star formation history, it means that we can just choose a random number when we do this Monte Carlo approach from time 0 to 10 billion years. Yeah? When we choose this time, we add it to this delay time for a system. We have merger time, and we check if it is below 9 and 10 gigayears if we choose delta t to be 1 gigayear. If it is, we count it. If it is not, we just continue. Yeah. Yes, yes. We will have the number of mergers within the last 1 gigayear. So when we will divide it by 1 gigayear, we'll have a number of merger rate for these objects. And of course, later on, we need to apply this scaling factor. And when we use a Monte Carlo approach, we cannot simply multiply by this scaling factor, but we need to repeat this sampling of star formation history a number of times, which can be calculated from this number and the total mass of a galaxy, which we assume according to this formulae. Yes. I think the number will be a best first result, just to see what's the number of what's the merger rate for these simple assumptions, and later on we'll try to improve these rates. This one? Yes. Yes. Actually, if star formation rate is some simple function like constant function, we can do it analytically. When we want some more complicated, more realistic star formation rate, then we need a real integration. Constant star formation rate is we have total mass for a galaxy of 3.5 times 10 to 10 solar masses, and we have the age of a galaxy of 10 billion years. Once again, these are simple assumptions, and these give us a star formation rate, but for sampling this birth time, we just need a probability distribution, so this function needs to be normalized, which is here, the normalization factor. Yes? Okay. T cure is a current time. So current present time, so we assume that it's 10 billion years for this simple model, that just age of a galaxy is 10 billion years. Yes? Yes? Yes. 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 So at the end here we have the evolutionary history of the system. So not all the lines have the same length. So that's something we maybe will look on at the end, these evolutionary histories. Yeah, sure. Yes. Yes, there are some ranges in which it is not working. Yeah, but yeah, for example, if the delay time of a system is nearly 10 gigayears, we have a smaller probability of seeing it than when the probability is lower than 9 billion years. Yeah, because then it will be just what you've written here. Yeah, current time, yes, which we assume just the age of the galaxy. Yeah, because we just need to choose a 0 point somewhere, and it's most convenient to put it at the. Okay, we can put it, but later we'll have to add these 3 gigayears. Yes. Yeah, so in trivial example, we just take 9 gigayears just to have a very nice numbers for calculations. It's current age of galaxy, of a stellar system we are investigating. Why? This part. In general, yes, but we use a simplified approach. For the sake of this calculation, it's, I think, 10, because it's the current age of the universe. Uh, so here we have the birth time of a galaxy, which we just put as 0 because we need a 0 point somewhere. We can put 0 here, and the birth of the galaxy will be at 3 or something gigayears. But we just, when we put 0 here, we just don't have to care about this time here. Yeah? Then we have current time here, which in this simple approach, we just assume that it's 10 gigayears. Yes. Yes, in more elaborated approach, it will be 13 or something. But when we want just this simple approach, later we can. And here we have delta t. Yes. Okay, so these formulae are very universal. Yeah. In our approach, this formulae just means that when we have a system which is born somewhere here, it just have the probability when we have some value of t del, the if we want a system to fall here, it needs to be born t del, t del, so it needs to be born in this part. Yeah, yeah, it will be exactly the same like delta t. So when we use a constant star formation rate, we just have this probability equal to delta t times 10 gigayears. Unless TEDIL is larger than 9 gigayears, then we need to improve this calculation. Yeah, but when TEDIL is larger, like for example this size, we cannot go as far because we'll be before the birth of the galaxy, so we need to lower this probability then. Yes, yes. So we have TEDEL, and if it is lower than 9 gigayears, yeah, we can stay with this simple approach. When it is larger than 9, we need to include this fact that we cannot go below 0. No, we need to check what's the probability. If TEDEL is larger than 9. If it is larger than 9, it means that here, well, and here, it will go below 0. So we don't want this to happen, so we want only these time births, which can give us correct merger time. Yeah, so we need to calculate what's here, what's this delta t prime, let's say, times 10 gigayear, and this will give us this probability for systems which are for which the delay time is above 9. And if the delay time is above 10 gigayears, what will be the probability? 0. Yeah, exactly. Million years. Exactly. You can check what's the separation of the system. Yeah, yeah, they are very high numbers for most of the systems, but I think that Chris made this argument that most of the black hole binaries which are made are very wide, and merger times are much higher than the Hubble time. Okay, yeah, so it's here, this simple formula. It does not take care about propagation time, about detection probabilities, and so on. Current time is just assumed to be 10 gigayears in this simple approach, like the age of the galaxy, the stellar system we are investigating. It's uh, it's just the case where we put time zero. We can put it currently and include negative times, but usually the most convenient is to put zero at the beginning of star formation. Yes. So, so I hope that at least this simple approach will be finished, but I don't know currently how it is going. And later on, I will stay here till the end of the week, so I think that yes, exactly, exactly. Yes, yes, yes. Minus here. Yes, because it's time current, and this delta t tells us calculations before. Actually, plus should change nothing, but just to have results comparable with all the others, just put minus. Yes. And 10 billion years when we put this simple assumption. Yeah, but you cannot choose this. You need to do a random sample using some random number generator. You are using Linux, I see, so you have a random number generator in your system. Or if you are using some yes, 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 and you need to calculate the scaling factor, yeah, from this number, this m sim, which is on a blackboard, and m total, because we need to make this size of a simulation. We need to make it the total number of stars we want to compare to, so our galaxy. So it will give us scaling factor. When we have a scaling factor, we need to repeat this sampling the number of time which this scaling factor tells us. So every system will take into account so many number of times, but for statistical reasons, we need to give them different birth times every time. it's not this one. T del is this one.
Yeah, I know.
Okay.
Tidal is this one, so it's
Yes.
Tidal. Temer is not T merger. I
No, no,
understand.
it's not T merger.
Okay. And but delta T, it's what? What is delta T?
So delta t, I propose to give it 1 billion years. We need it just to make this calculation here. Yeah, delta t, delta t. In ideal situation, we will do a limit here. Yeah, and put both these values to 0, and we'll have an exact merger rate at the current time. But it's not possible due to numerical reasons. We need just to put some value here and value here. We obtained an average merger rate in this time, delta t. So we don't want it to be too large, because average merger rate throughout 10 billion years may change. The merger rate may change significantly. And we don't want it too small because of these statistical and numerical fluctuations. Yeah, because to make it small, we'll need to have the infinite number of data records, yeah, to have the correct value. Otherwise, if you lower this delta t, you can see that the number of merger rates will fluctuate strongly.
Okay.
Yeah, so this what I propose gives some stability, numerical and statistical stability, whereas 1 billion years for constant star formation is something which give us nearly the same merger rate like for smaller time.
Okay. Okay. Merci.
Yeah,
Thanks.
thank you.
I'm kind of lost. I just read the table, so I have the file here.
Yes.
So each line has these
Yes.
different values here that you're
Yes.
putting.
Yes. Exactly.
Okay. So what I don't understand, each line is the result of a multicolor simulation.
Tak, for the system which formed a double compact object.
Okay.
So each line is a different double compact objects, and parameters like this mass, separation, delay time, chirp mass are calculated at the moment of the second supernovae, so the formation of double compact object. Yeah. So this delay time is calculated for you from this formulae for the angular momentum loss in gravitational waves. Yeah. So you don't have to do it. You just need to include this delay time to see if these double compact objects will merge within a Hubble time, because if it is too wide it will not merge, so we just need to throw it away, we will never see it. But if it is smaller than Hubble time, it is a probability that it will be born in a time
That we
when,
could see it
yeah, and the birth time plus the delay time will give us this merger time within this reasonable past, like 1 gigayear for
Okay.
this simple approach.
And how do I calculate this?
So this is a formulae in this box. We have a number of double compact objects for which T merger is between T current, which we can assume like 10 gigayears, so the age of a galaxy, and delta T, which we just need for these statistical reasons. Yeah? And so if it is within these limits, this T merger, which is calculated like T del plus time of birth, and time of birth we need to get from the star formation history, which for this simple approach we can assume that it's constant throughout 10 gigayears, so any birth time is equally probable.
Okay.
So we need to see what's the probability that the birth time will be correct for the system to merge within this delta t from the current time. Otherwise, we can sample through random numbers what's the birth time of a system, add it to the t delay from the sample, and if t merger is within our range, we count it in this n DCO. If it is not, we go forward without counting it. And we need to repeat it, this sampling, for the factor which we get from the scaling. So we need to divide total stellar mass of the simulation, which is this 3.5 times 10 to 10 solar masses, by this simulational mass. So we simulated only 7.3 times 10 to 8 solar masses, whereas what we want to compare to is 3.5 times 10 to 10 solar masses. So we need to repeat this sampling for any system the number of time which is given by this scaling.
Okay. But
Yes?
is this what I don't understand? We have to do the sampling here.
Yes, yes, that's the problem we need to solve, exactly. The mathematical problem, yeah, because physics in this simple approach is simple. What's the problematic is just to get these birth times and scaling factor and calculate these merger rates.
Okay. Okay. Thank you.
Okay. Yes? No problem.
As I understand, T current is 10 gigayears,
Yes.
and delta T is 1 gigayear.
Yes, yes, that's what we assume in this simple approach.
Yeah. So in the file, we need to find the number of columns which have T merger in between this range, right?
Exactly.
And we need to count how many
We,
are there.
we need to count them. And T merger is calculated this way. It's not T mer from this file.
Okay.
Yeah? And T birth is this way what we need to calculate from statistics.
Okay.
But when we assume that the star formation is constant,
Okay.
any time birth is equally probable, so we can use Monte Carlo sampling, simply just taking random number from between 0 and 10 gigayears.
Between 0 and 10 gigayear.
Yes,
Flat random distribution.
yes, flat random distribution, because the star formation rate is constant, so no time is preferred for star formation.
Okay. So T birth will then be equal to some number in between this
Yes,
range,
we need
randomly
just to
sampled.
randomly sample this space. We cannot choose this number. We need a random generator
Yeah.
to choose this number differently for any record
Okay.
in your file. And
And then we calculate T merger for every sampling.
yes, yes. And
And
if
then
it is in this limit, we count it
count.
to this number. If it is not, we go forward.
Okay.
And we simulated only 7.3 times 10 to 8 solar masses, whereas the Milky Way mass is 3.5 times 10 to 10 solar masses.
Okay.
So we need to scale these results which are in the file through factor which is m star total divided by m star simulated.
Okay.
Yeah, this gives us some factor of scaling, and we need
Scale what? We should scale what?
and then we should repeat this sampling
Okay.
the number of time which we get from this scaling.
Okay.
And every time we need a different birth time. We cannot take the same because we will have a huge statistical error which will give us strange results.
And this would give the number of what
Number
would
of
you say?
double compact objects which merge within the current time and 1 gigayear before.
Before.
So if we divide it by 1 gigayear, then we get an average merger rate through the last 1 gigayear, because we have number through time. So merger rate of these objects.
And this would be used for what?
So it's what we have to calculate, yeah, to see what's the merger rate for such system like our galaxy with this simplified approach.
Okay.
And then we check it for the lower metallicity, this 10% solar,
Okay.
yeah, and we can check how it differs for black hole systems, black hole neutron stars, and neutron star system. Yeah. Okay. Here you are.
Sorry.
Yes.
So, T birth, how are we actually supposed to assign this for each system just from the probability distribution?
Yes, exactly.
Okay.
Because we know that stars, for this simplifying assumption, forms uniformly throughout these 10 gigayears. Yeah. So any birth time is equally probable. Yes, so we have just a uniform distribution of birth times through these 10 billion years. And either we calculate this probability that the birth time is correct for our computation in this way. Yeah, we just check if this probability, this lower one, for our system is above 0.
Okay.
Yeah. Other way, which is simpler, I think, for constant star formation rate, is just to use a Monte Carlo sampling. So you take a random number from between 0 and 10 billion years and you assign it to this record, but later on you need to apply a scaling factor. Yeah, because we simulated only 7.3 times 10 to 8 solar masses, whereas the total mass of the galaxy to which we want to compare is 3.5 times 10 to 10 solar masses. This gave us a scaling factor. Yeah, and when we do a Monte Carlo sampling, we cannot simply multiply our results by this scaling factor. We need to repeat this sampling the number of time which is given by this scaling factor. Yeah, because if we will just multiply, we'll have a huge statistical error. By repeating this sampling, so the same record, we have different birth times with different repetition of the calculation, yeah, then we'll have a much better, statistically much better result.
Sorry, so what do you do with the repetition?
Okay, so there are about 8,000 records in this file when you do black hole merger rates. So you go through all these records and apply a birth time to all the records. Yeah. So some of them will go into these n double compact objects for this computation, and some of them will have too high or too low this time. Yeah. So and then we do another another repetition of this procedure, and we apply again random birth times which are not equal to the previous times. Yeah, they are different, and we repeat this procedure till we have a stellar mass of 3.5 times 10 to 10 solar masses. Each repetition gives us only 7.3 times 10 to 8 solar masses. About, yeah, so it's easy to calculate that it's about 50, 48 something, if I'm right. Yeah, so I think it's simpler, but you can also calculate what's the probability that some system will fall within this range, T current minus delta T to T current. So within 9 gigayears and 10 gigayears. And then you don't have to repeat this again and again. You just can multiply by this scaling factor.
Thank you.
Okay. Sorry, I will go and return to you.
I'm trying to understand the strategy.
Yes.
So basically, since the star formation is a constant,
Yes.
have to generate a number, a random number, between 0 and 10 gigahertz for the formation of each star.
Yes.
Okay. And then to the biggest number, we look what is the biggest number between these two, and we add to the biggest number this time delay,
Okay, why biggest number?
because we need that both the stars are born between before exploding.
Okay, I try to explain it, but maybe I do it wrongly.
I wasn't following. So
Yeah.
probably the
Okay, so in population synthesis studies, we made no interaction between different systems. So we assume that all binaries are born at the as a binaries. So they are not made dynamically.
Okay, so I only need to generate one, and
Yes.
then at this time, and
Exactly.
if this the sum of the two is bigger than the age of
Yes.
periods with the
Yeah, that's this limitation of population synthesis, but for some sparse stellar systems like galactic disk, it's thought to be correct.
Okay, thank you.
Here. Yeah.
Downloading the data.
Yes.
But the seventh element, which should be T del, is 10 to the 7. But it's, here it says that it should be in units of mega years. Am I
Yeah.
taking the correct data?
Yes.
This is what the first element looks like. This should be the first element of all the
Yes.
bar counts. So the seventh one is this one, 10 to the 7.
Yes.
Is that the T del?
So check what's the separation. Separation is 30. Yes, solar. It's the third parameter.
Yes, 30.
So where we have two neutron stars, because I see that you use neutron stars, yes, and we have such high separation, the merger time is very high. Yes, so it can be so. And such systems will never merge within Hubble time, whatever their birth time.
Okay, so I picked the wrong data if I wanted to do.
It's just a record which is useless because it will never merge within Hubble time. Yeah? So such records you just skip and go to some which have a merger time below 10 gigayears. Yeah, so it's okay. Yeah. I will just talk to the organizers and go back to you. So we need to end in 5 minutes, yes? Yes, okay. Okay, so we will end and I will just say that we can do it later on. Maybe just they need to...
Promise the answer.
Yes.
The answers are in this article, yeah.
So provide the column number.
Yeah, maybe just maybe I assume that it's simple, but it's not.
I think they
So
got confused. Or they did not. It was not clear at the end what they had to do. They had to compute, So
yeah, so maybe I assume that they have done some merger rates before, and they were no merger rates calculations.
yes.
Yeah. Okay, so assume that it's
If you can write out a summary of what they were supposed to do and what the results are.
I think that would.
I just make a PDF and I put it on the web.
okay. Okay. Okay, so that I haven't been from the beginning, so I assume that they have the background.
No, I mean the staff folder.
Okay.
So if you can provide, tell them that you will provide the answer.
Okay. So these PDFs will be later on a web page, yes? Because I've seen. So I will extend this PDF with some explanations better, because I just assumed that it's too simple for them,
Okay.
yes?
It is when you know
Yeah. Okay, so I will extend this PDF and I will say that I will be here till the end of the week, so they can just, maybe they just need more time, yeah, than 1 hour. Okay, so thank you. Okay, so we are ending in 5 minutes. So I will be here till the end of the week. So if you will like to end this exercise and compare your results or ask about something, I will be happy to help you. I was also told that you have done nothing similar before, and I assume that I will start with something very simple. So I will extend this PDF with the exact information of what should be done to calculate these merger rates and other interesting things, and it will appear shortly on a web page. Yeah, okay. So thank you, and if you have